In these next two videos, we're going to look at a topic which is known as mechanics of muscle contraction, and I suppose you could argue that this is really a biomechanics topic, but that's okay. It doesn't hurt for you to get it more than one time. And so as we think about muscle mechanics, it might be helpful to think about a couple of different questions. And one question, why is force generated by a muscle not always the same? Here you can see Brian Shaw. This guy's a giant of a man, and he's actually won the world's strongest man competition on several occasions. Here you can see him raising a spoon of food which weighs ounces from a bowl up to his mouth, and he is using the flexors at the elbow to do much of this. Here you can see him curling a dumbbell, which I can only imagine is pushing 200 pounds, but again, he's using the flexors at the elbows to do this. And so you can see that the range of force that the same muscle group is generating is absolutely tremendous. And so you might wonder why that is. Why is it that a muscle can move a load at times, but at other times it can't move that same load? And so these are some of the questions that we'll think about as we talk about this. And we refer to what we're talking about here as gradation of muscle force. Gradation is the somatic nervous system regulating the level of force output for a given muscle or muscle group. And the truth is that almost every move that you do is controlled by a group of muscles and not just one. Even when you do something like arm flexion, it's actually biceps and brachioradialis and brachialis. And so a number of muscles. Do the following thought experiment to help you understand what we mean by force gradation. Go into the weight room, stand there in front of the dumbbell rack, and I know you can't do that right now. Take a 5-pound dumbbell, curl it, set it down. Pick up the next one, a 7.5-pound dumbbell, curl it and set it down. Go to the 10-pound, curl it, set it down. Do the 12.5-pound, curl it and set it down. And then the 15th pound, and continue to do this until you get all the way down to the end. And you know that some people are going to be able to curl well over 100 pounds. And you can see that we're grading the force depending upon how much the dumbbell weighs. And so you have these very light dumbbells that don't require much force at all. You have moderately heavy dumbbells which require more force to come from the arm flexors. And then you have these incredibly heavy dumbbells which require a tremendous amount of force. There are two mechanisms that are responsible for gradation of muscle force. And the first and hardest to understand is what's referred to as rate coding. And this has to do with how frequently we send action potentials down the alpha motor neurons to the muscle we're looking at. The second mechanism that we use is what's called motor unit recruitment. This is much easier to understand, and this has to do with how many motor units are being activated when we do what we're doing. And so when you take a 5-pound dumbbell and you lift it, it might only be 2, 3, 4 motor units. When you do 100, it could be 300 motor units that are being activated. Just real quickly before we move on, we're going to look a little bit at some muscle physiology stuff. Much of what this is all based on is actually using animal models where the muscle has been taken out of the body. Here we see what's referred to as an isotonic contraction. Iso means same, tonic means tension. And so you can see we've fixed one end of the muscle, so it's not going to move. The other end of the muscle is attached to some kind of a resistance, and then we stimulate the muscle and it contracts, and in this case it's able to raise the weight straight up. Since we're not dealing with a skeleton or a lever system, it is a constant tension throughout this contraction. When it first started to move the weight, the tension was the same. As it moved it further and further, the tension is the same. Here we've changed things a little bit by adding a weight which is actually in excess of the maximal force that can be generated by the muscle. And so now again the muscle is stimulated, but it doesn't shorten at all. And so this is what's referred to as an isometric contraction. Iso, same or constant metric length. And here you can see the tension that we're talking about here for those two things. In fact, often what we do is we do attach the muscle to a lever system that we use to raise the weight. And now in this case, it can't be isotonic. When we use levers, we change the moment arm, and that changes the force that's required. Here you can see an actual nerve muscle prep, and so here is a frog gastroc that's been put into a clamp, and then we have, you might be able to see that cord or wire there that fixes it to the other end. Here's a schematic representation of this. You see that we also have this gear that we can use to adjust the length of the muscle. If we move it down, the muscle is actually getting shorter. When we move it up, the muscle is getting longer. And then here we can stimulate the nerve. This is the whole nerve, including all the alpha motor neurons that are going to this thing. And then when we stimulate it, we get it to contract, and we can actually record the force that's been generated by this thing. When we talked about a muscle twitch already when we looked at fiber types, and so I hope you remember some of this. A muscle twitch is gotten in a single motor unit or a single muscle fiber, and it's in response to one single action potential or one single stimulus, and there you can see it. And so in response to this action potential, the muscle contracts, it reaches some peak tension, which isn't really maximum, it's only maximum for this twitch, and then it relaxes back down to zero tension. And here again you can see the time is in milliseconds. It's not even taking 50 milliseconds for this twitch to occur. The tension is also in millinewtons, because again, this is just a few muscle fibers, perhaps even just one muscle fiber. Here you can see a muscle twitch again, and as I just told you, this isn't really maximum tension. It's only maximum tension for the twitch, but not for the motor unit. Here you can see a stimulus and the resulting twitch that we get. We let it relax completely, and here is another twitch. Here's another stimulus and a second twitch. Now these twitches aren't great because this is a little bit more accurate. You can see that the relaxation time, in fact, is longer than the contraction time, and that's what we normally expect to see. So these twitches are a little bit off. Relaxation time should be longer. But notice the peaks. And so this shows what we refer to as all or none for twitches. We get a muscle twitch, we let it return to zero, we give it some time to recover, we give it a second stimulus, and so the twitches look relatively the same, all or none, all or none. Now you see what we're going to do here is the second stimulus comes before the motor unit has had the chance to return back to zero tension. And now you can see that the tension adds. So you can begin to see that this isn't the maximum force. We can get more force. If we gave it a third action potential here, it would add on again and again and again up to some new maximum. And now we're starting to get the idea of what we refer to as rate coding. In this particular case, the action potentials have come so quickly that they come every, I would say, every 12 or 10 milliseconds before there's any decrease in tension whatsoever, no decrease. And so the rise in tension is nice and smooth, and we get to a true maximum. We can't get any higher force out of this motor unit than what you see here. And this is, in fact, what we would refer to as a complete tetanus or a fused tetanus. Same thing, complete or fused tetanus. Here we see a different depiction of what we just looked at. And so here you can see we give it a stimulus, we wait, give it a second stimulus, we wait, a third, and then finally a fourth. And so these are our twitches. We've shortened the x-axis a little bit so that 40, 50, 60 milliseconds is right here. Now what we're doing is we're giving it multiple stimuli before it relaxes completely. There should be multiple arrows in here if the arrow is representing the stimulus. 1, 2, 3, 4, 5. And so now you can see that the tension is higher than it was for the twitch. Here we're going to give it 1, 2, 3, 4, 5, 6, 7, 8, 9, somewhere around 10 that come even closer together than these did. And so now the tension is even higher. Here we're going to give it about 10 again, but we're going to stimulate it even more rapidly. And then here you can see that we're stimulating it more rapidly than every 15 milliseconds. And so the force goes up in a nice smooth manner and it hits maximum force. And again, getting more force out of a motor unit by stimulating more rapidly is what we mean by rate coding. And this, in fact, is one of the things that you were doing as you were lifting dumbbells that were heavier and heavier and heavier. You were doing some rate coding. And here you can see, here's the frequency at which we stimulate the muscle, and here is the percent of maximum force that we get. And so this is a different way of illustrating the rate coding, but we're not seeing a complete tetanus, and we're not seeing incomplete tetanus either. Here's a slightly different way of illustrating that. I don't like this figure quite as much because the twitch is too long. It should be back in here somewhere because, again, it's going to be less than a half a second for the twitch to occur. And then there's an unfused tetanus. And so we're stimulating, but we're letting the tension drop a little bit before the next action potential comes. Here's a second unfused tetanus. But now the stimulation rate is a little bit faster, and so the plateau is at a higher tension. And then finally, here's a complete or fused tetanus. And we cannot get any more force out of this motor unit than we're getting with our fused tetanus. Okay, and so now again, I have to reiterate that the action potentials are coming faster than every 15 milliseconds. There's no drop in force whatsoever. Here again, we've done the same thing, but we're superimposing this on one another. Here are the twitches, and then we get 1, 2, 3, 4, 5, 6 unfused tetany. And then finally, the green one, I believe, is supposed to be a fused tetanus, and so that represents the highest force that we can get from this particular motor unit. And then here is just a different way of depicting that. Here you can see this is where you're stimulating it and we're getting twitches. And then we get an unfused tetanus, unfused at a faster and faster frequency until finally, we get to our fused tetany. And here you can see it doesn't matter what the speed is after that, the fused tetanus doesn't get any higher. Once you hit fused tetanus, that's it. We can't get anything more out of this guy. And so again, we're looking at rate coding here. That's what we're doing. Rate coding allows us to get the maximum force possible out of this motor unit. And so here you can see that the twitches are, I don't know, you estimate, I would say 20, 30 millinewtons. And here you can see that the fused tetanus is, I don't know, 150, 180 millinewtons, somewhere somewhat less than 200 millinewtons. Okay, and again, here you can see the same type of thing. And so now we have our twitch. And all they're showing you is the relaxation time. And so you can see that the total twitch time looks like it's maybe somewhere around 60, 70 milliseconds. And don't ask me why they don't show you the peak force, but you can see that the peak tension looks to be somewhere around, I'm going to say 130, 140 millinewtons. And then again, you can see unfused tetanus 1, unfused tetanus 2, and then complete tetanus. And so look at the complete tetanus. So now it's going to be 200, 300, maybe 380, 400 millinewtons. I can't be sure. But you can see that the total time is considerably longer. And here you can see the same thing again. And here's a twitch. And then here, unfused tetanus 1, unfused tetanus 2, unfused tetanus 3, and then fused tetanus. And now what is our peak force here? 50, 75, maybe not even quite 100 millinewtons. So explain the differences here and here. I hope what you looked at and said was, well, this one is much slower. Looks like it's about 80, 100, it's over 100 milliseconds, and it's only going to about 10 millinewtons. So I think that this must be a type 1 muscle fiber, and this must be a type 2 muscle fiber. I don't know if it's 2X or 2A, but it looks like it's a type 2 fiber. And so there you can see the differences both in twitch, in fused tetanus, and also in unfused tetanus as we look at that. And then we did start to talk a little bit about motor units before. A motor unit, again, is the alpha motor neuron and all the muscle fibers that it innervates. These aren't great depictions. I don't think there are any examples of motor units that only have 2 muscle fibers in them, or motor units that only have 3 muscle fibers in. It's possible. This is slightly better. And so here you can see the alpha motor neuron. It begins to branch. Here are the telodendria. Well, actually down here are the telodendria. These are collateral axons. And so you can see that we're going to go to at least 1, 2, 3, 4, 5, 6, 7, 8, 9 motor units. And so this is a somewhat better depiction of a motor unit. And so a motor unit is the alpha motor neuron and all the muscle fibers that it innervates. And what's true of one fiber in that motor unit is true of all the other fibers. And so if we send an action potential down here, it's going to go through all the collateral axons and all the telodendria so that all muscle fibers will receive that action potential and in response will at least get a twitch, if not in unfused tetanus or fused tetanus. All the muscle fibers in a unit are of the same type. And so for this green unit, if this is a 2X, all of them are 2X. If it's a 2A, they're all 2A. And if it's a type 1, they're all type 1 muscle fibers. You can't have a mix of fiber types in a motor unit. Here you can see some estimates of how many motor units you have in a given muscle. And so here's abductor hallucis longus to move your big toe, but almost 300 motor units. Biceps brachii is only a little over 100, but here we combine it with brachialis. Again, remember that these two work together to cause flexion at the elbow, and now we're over 350 motor units. And the plantar flexors, soleus and gastroc, we're pushing 200 motor units. I don't expect you to memorize these values. I just want you to know that most muscles, several hundred motor units, not just 1 or 2, but several hundred. The innervation ratio seems to range from a low of about 5, and these are estimates too, upwards of about 2,000 muscle fibers within a single motor unit. And so you can see that number ranges quite a bit. Here you can see rectus lateralis only has 5 muscle fibers in there. That's what we mean by innervation ratio. 1 alpha motor neuron, but only 5 muscle fibers. Rectus lateralis is what will move your eyeball to the side. So sit there and look to your right without turning your head. Rectus lateralis has to move your eyeball to the right. And so not surprisingly, you need very, very little force, but you need some good motor control. Okay, and then tensor tympani, it controls the small muscles of the inner ear. The muscles that control your fingers will also have relatively small innervation ratios. And then look here, the gastroc is one of the stronger muscles in your body, and it's pushing 2,000 muscle fibers within a given motor unit. Again, I don't expect you to memorize this, but muscles that have to generate a whole lot of force are going to have big motor units. Muscles that are responsible for fine motor control are going to have smaller motor units. All right, and now we need to look at, we just looked at rate coding, now we need to look at motor unit recruitment. And so here you can see experimentally we have 5 motor units, and initially these are the action potentials in the motor neuron controlling that unit. And so only motor unit 1 is active, 2, 3, 4, and 5 are inactive. The force output is very low. Now we activate 1 and 2, you can see that 1 stays activated and 2 is brought in. Then we activate 3 and 4, and finally we bring the 5th one into play. And so now you can see that the force is getting higher and higher as we activate more and more motor units or recruit more motor units. Now look at how they fall out. When we start to deactivate motor units, the last one in is the first one to be deactivated. And then number 4 and 3 get deactivated, and then 2. And so again, finally 1 is the only one that's left being activated. And so presumably this one is a type 1 fiber, and perhaps they all are. We don't know for sure, but that one for sure would be one. And so as more force is required, we activate more motor units. And that is what we mean by motor unit recruitment. And we do get this orderly recruitment that was laid out by Henneman. He talked about the size principle, and he's talking not about the size of the motor unit, but the size of the alpha motor neuron cell body. And again, this is what we talked about when we first talked about first talked about fiber types. And so here's the type 2X, and the soma is pretty big. Here's the 2A, and the soma is still big, but not as big. And here's the type 1, and the soma is the smallest of all. And so it's easy to get from an EPSP here around to an action potential at the trigger of the zone. And so these are the more easily recruited motor units and muscle fibers. And so we bring the type 1 into play first. And we also think that there is a relation between recruitment and power output. At very, very low power output, all we use are the type 1s. As the power output goes up, we use type 1s and some 2As. And as it goes up more, we use 1s and more 2As, and then we start to bring in the 2Xs. And so that's always what we thought used to happen. But now some researchers have gathered some data looking at cats and what's referred to as a paw shake response. And so if you take a piece of Scotch tape and you make a loop that's inside out so that the adhesive is on the outside, stick it on the paw of the cat doesn't like it, and it will flick its paw as fast as it possibly can. It'll do it once, it'll do it again, trying to get the tape off. These cats, the shake is so fast that the paw is a blur. And that's because they have type 2Bs and type 2Xs. Humans have 2A, 2X, but we don't have type 2B. And those guys can go like crazy. And so some researchers started to question, is that also true for humans? And so again, what we used to believe was you do something like a vertical jump, you're recruiting all of these guys. Again, remember the type S are the type 1, the FR are the 2As, and these are the 2Xs. And so that's what we've always thought for a long time, and now we're not sure. We still need to research this some more, but conceivably when you do something that's really high power like vertical jump, you might jump right over the 2As and the 1s to get right, I'm sorry I did that wrong, jump over the type 1 and the type 2As to get right to the 2Xs, and that's what's responsible for vertical jump. You don't need maximum force like when you do a 1RM squat, you need relatively high force applied really rapidly. And so that's the question. Maybe this is not what we do with real high force. Clearly, this is what we do with a 1RM. With a 1RM, you're going to recruit as many motor units as you possibly can, and you're going to do rate coding. You're going to stimulate them very, very rapidly. And so that's what's going to happen with something like a 1RM. With a vertical jump, still a big question mark. Something we need to look at. That brings us to the end of this video. In the next video, we're going to talk about a couple of important relationships. One is the length tension, and the other is the force velocity relationship.